basically, so if I want to take P of A, B, and I want to eliminate B, then I essentially collapse them by adding up the rows where A has the same value. That's it. So I did two things. One is I told you about factors, and I told you about multiplying factors. I also told you about eliminating variables from the factors directly. So in essence, you can do this idea of variable elimination, which I'm not going to discuss at any length here, automatically in terms of directly factors. And whatever factors such as these that you compute, these you will wind up storing intermediate results so that you don't have to recompute them. That's basically the best algorithm for exact inference on Bayes networks, variable elimination. And the interesting question, of course, is these factor sizes keep increasing and reducing as the algorithm goes on. Do you see that? Suppose my algorithm, my final question is, what's the probability B given A? It's just going to be two numbers. Right? But in doing so, you may need to wind up generating the entire joint distribution and then eliminating things out. So the space requirements are actually dependent on what is the largest factor that you generate and store. And it turns out that from the point of view of the size, the order in which you eliminate variables winds up mattering. If you eliminate them in the right order, you would have the largest factor you will ever get might be much smaller. If you eliminate in the wrong order, you might wind up doing big. This should not be surprising to you given what we just saw here. So, for example, if you eliminated, and also the time you eliminate, right? Basically, if you eliminated the variables by pushing them inside, the summations inside, that reduces the size of the factors you keep around. If you put all the summation outside, that is effectively generating a 16 size matrix and then adding them. So obviously your question is, can we not figure out what is the optimal order of eliminating variables? Yes?
Yes.
It would be
Matrix multiple.
NP hard. Anytime there is an easy way of getting by, you'll find it hard. Okay. It turns out optimal order of elimination variables is NP hard. The heuristic that does work is to eliminate variables in the reverse topological, reverse causal order. That would work very much. Yes?
Variable elimination or the factor?
No, it's ultimately the question of elimination.
Okay, so you just eliminate that first cost.
Yeah, because the thing is that in this case it was, in this case it turned out that the only reasonable order is to eliminate A first and then eliminate E.
Yes.
In some cases, the summations might be such that I could use different orders in which to eliminate.
Oh, okay.
Yeah.
And then which one is the right one. Either way, when there is no ambiguity, that might also tell you that the network is happy network. And we know this network is a happy network because this is a singly connected network. But variable elimination algorithm should work for any arbitrary network. And when it's multiply connected, actually there will be ambiguity. And the right order winds up making a difference. Okay? That's as deep as we want to go into this.
I just have one question.
Yeah.
So you said a good heuristic is eliminating variables in reverse causal order. When you say causal order, do you mean the causal order of the graph?
Yeah, causal order of the graph. Yeah. Basically, again, even though we know that the arrows are not causal, we once in a while say they're causal.
Sure.
Okay. Okay, so I am going to move from here to a different topic, which is kind of more fun and also easy because as time goes on, things become harder, right? So That was as good as hard as base network became.
It probably
And
won't be
we are
recorded
now
because I'm
going
almost
to-
out of power too.
Whatever.
Did you pick the optimal order?
I don't know this now. Oh, this is what. Okay, somehow it is showing there, it's not there. Let's see.